Hello, this is Mr. P, and today we're going to learn about properties of logarithms. These properties are going to go hand in hand with our laws of exponents, so if you know the exponent laws well, then these will be very similar. Now, for our properties, when we use the letters A, when we use the variable A, just like our discussions before, A is going to be a positive number that is not equal to 1. And for the u and the v, as long as those are positive real numbers, then we have the three following properties that can allow us to either break up or combine logarithm expressions. So first of all, if you have the log of a product, in other words, the argument is a product of two factors, then you can break that up into two logs of each of the two factors. So log base a of u times v is log base a of u plus log base a of v. The equivalent notation in natural log would be ln of uv equals ln u plus ln v. They're both the exact same idea, but remember that natural log is basically log base e. A would be e for the natural logarithm. Now the quotient property also allows you to break it up if your argument is a quotient, and that would simply be the log of the numerator minus the log of the denominator. So it would be numerator minus denominator. And again, they would both be in the same log base a. And finally, the power property allows us to get variables out of exponents. If we have log base a of u to the n, then we can take that n and think of it as moving it out to the front, so it's n log base a of u. And likewise, we also do have the natural log version, which you will be using more often than the base a. When you get to higher math, but natural log of u to the n is n natural log of u. All right, let's look at a direct comparison, though, between these properties and the laws of exponents. I want you to be able to see the similarities and understand that they're basically saying the same things here. Notice on the first one here, we have the log of a product is equal to the log of the first factor plus the log of the second factor. Well, that stems from the fact that if you multiply powers, you keep the base and add the exponents. Notice how logs are exponents, so if we're multiplying, we're going to add the exponents. We're multiplying inside the argument. That means we're adding the exponents because the log is an exponent. Likewise, if we have a to the m divided by a to the n, if we did our law of exponents there, you keep the base and subtract the exponents. So for division in your argument, you're going to subtract the exponents. Again, remember that logs are exponents. And the last one basically stems from the fact that a power raised to a power is going to be keep the base and you multiply the exponents. So here the r is an exponent of that argument and the log itself is an exponent. So basically we're multiplying the exponents here. R is an exponent, log is an exponent, so we're multiplying the exponents. Or physically, when you get into the algebra and manipulation, you can think of it as just being able to take that R and move it out to the front. Alright, so let's look at a proof of a couple of these. We're going to prove the first one here, and we are going to prove the last one. The proof of the second one is laid out the same way as the proof of the first one, so we're just going to prove the first and the last. All right, for the first one, we have the log of the product is equal to the sum of the logs. We're going to start out by saying that we're going to let x equal log base a of m. We're going to set a variable here, and we're going to let y equal log base a of n. So both of these equations, we have x equals log base a of m, y equals log base a of n. We're going to change these from logarithmic form to exponential form. And remember here, a log is an exponent. So this is saying that the exponent of a that gives you m is x. That means that a to the x is m, because the exponent of a, which is x, gives you m. Same thing over here, we have a to the y equals n. Those would be the exponential forms. So now we're going to take our original equation here, and we're going to substitute in these two expressions. So since we have what m is equal to, what n is equal to, we're going to take this left side here. Log of the product is the same as the log of m times n, because a to the x is m, a to the y is n. And now we can use our law of exponents to say if we're multiplying powers, we keep the base and add the exponents. So this is log base a of a to the x plus y. Well, if we remember our log properties from the previous section, which would be the inverse property, we can get a cancellation here, and that is equal to just x plus y. But since we said x is equal to log base a of m, and y is equal to log base a of n, then we can say, therefore, what we started with is going to be equal to x plus y, which is log base a of m plus log base a of n. And we're done. Now for the division property, that one is going to be, or the quotient property, that one is going to be proved basically the same way. We set x to equal log base a of m, y equal to log base a of n. The only difference here is you'd have the division in the argument here, which would change this to a subtraction, this to a subtraction, and this to a subtraction. Other than that, everything else would be exactly the same. All right, so now the only one left to prove is the power property. And when we prove the power property, we're going to take a similar approach. We're going to define a variable, let x equal log base a of m, which means we can rewrite this in exponential form, which would be a to the x equals m. You know, the exponent of a that gives you m is x. And then we're going to take what we're trying to find an expression for, log base a of m to the r, and make the substitution for m. So m is a to the x. That's log base a of a to the x times r. And when you have a power to a power, you keep the base and multiply the exponents. So log base a of a to the r times x. And then we have our nice little cancellation using the inverse property, which leaves us with just r times x. But we said x at the beginning was log base a of m, so making the substitution. Therefore, we get log base a of m to the r is equal to r times log base a of m. And we're done. All right, so these properties have been proven. We can now be confident in being able to use them. So let's look at a couple of problems we'll be able to do. Two things you need to be able to do is you need to be able to break a single log expression up into a sum or difference of logarithms. And you also need to be able to do it in the opposite direction, which is take sums and differences and combine them as a single logarithm. So first, to break them up, we're going to find that in using these properties that I have found it easiest to use the product property and the division property first, and then the power property at the end. So here, looking at this expression, we do have multiplication, we do have division, and we do have some powers. So of the three, I've actually found using the division property first is the easiest part. So we're going to break this up saying this is going to be the log base a of the numerator minus log base a of the denominator. That was simply using the division property. I'm sorry, quotient property. And now, after the quotient property, I'm then going to break up, this is a product, x cubed times the parenthesis to the power. So now next I'm going to use the product property, and that would be like this. For this product, it's going to be log base a of the first factor plus log base a of the second factor, so breaking up the product. And now the only thing that would be left is the power property. And that would simply mean I'm taking the power of the argument and moving it out to the front, so it'll become a coefficient. So this first term becomes 3 log base a of x. This term, when I move the 1/2 out, becomes 1/2 log base a of the quantity x squared plus 1. And when I move the 4 to the front, it becomes minus 4 times log base a of the quantity x plus 1. And we're done. I have found through experience, although you can use the properties in any order you want, product property, quotient property, power property, I have found that when breaking them up, when taking a single logarithm expression and breaking it up into sum or difference, I found it best to use the quotient property first, then the product property, then the power property. And when putting them together, I found it easiest to use them in the opposite order. I would do the power property first, then product property, then quotient property. And we'll see that in a later problem. So now let's let you try one. This will be your problem, and this time we're using natural log. But the directions are the same. Go ahead and break that up into the sum or difference of logarithms. And you can go ahead and pause the tape, work the problem, and when you're done, then you can come back. All right, hopefully you have an answer by now. If we look at the properties we can use, again, we have all three of them possible here. So I'm going to use the quotient property first. So that would be the natural log of the numerator minus natural log of the denominator. And then for the first term, I'm going to use the product property. And for the second term, I'm going to use the power property. So breaking this up, we will get natural log of x plus natural log of the quantity x plus 2. And then for this one, using the power property, I'll get minus 2 times the natural log of x plus 3, the quantity x plus 3. And nothing else can be broken down any further. No other properties can be used, so this is as simple as it gets. And we're done. All right, let's look at also trying to be able to use these properties to manipulate and simplify some expressions as a single logarithm. So first of all, I have a coefficient here, which means I can use that power property. Remember I said I like to use the power property first, then the product property, then the quotient property whenever I'm trying to combine as a single logarithm. So pulling the exponent, the coefficient up into the exponent of the argument, I would get natural log of 8 to the 2/3, excuse me. And then also I notice in the argument for the second term, there is all numbers. It's all numerical. So we can go ahead and evaluate that. 3 to the 4th would be 81. 3 times 3 times 3 times 3 is 9 times 9, which is 81. And then minus 8 is 73. So my first line here, I'm moving that up using the power property. And then I'm simplifying the argument here, which would be natural log of 73. Now, 8 to the 2/3 power, that can be simplified as well. Because, and this might be a little bit of review from Algebra 1, but if you have a fractional exponent, then the numerator is the power, and the denominator is the root. So fractional exponents are always power over root. And you can do these in any order you want. I could square 8 and then take the cube root, or I could take the cube root and then square the result. I generally find it easier if you're able to take the root and have it come out evenly, then go ahead and do the root first, because then you'll be working with smaller numbers. So rather than trying to figure out the cube root of 64, it's easier to take the cube root of 8, which is 2, and then square it to get 4. So we have natural log of 4 minus natural log of 73. And now the minus here is what tells you that you're going to use the quotient property. So it's going to be natural log of 4 minus natural log of 73 means that this is going to be your numerator minus this is going to be your denominator in your argument. So your final answer will be natural log of 4 over 73. And we're done. All right, let's give you one to try. And we'll do it a little differently, or a little different format, more general with the expressions rather than the numbers. So here you have u and v. It's 3 log base 5 of u plus 4 log base 5 of v. And we should note also that these properties, for these logarithm properties, these bases do have to be the same. They're both log base 5. All right, so in the first one, we're going to use the power property. That's the first one I like to use if possible. I'm going to pull that 3 up to be an exponent of u. And I'm going to pull the 4 up to be an exponent of v. So that gives me log base 5 of u cubed plus log base 5 of v to the 4th. And now the only thing left is the plus here tells us that we have the product property. So I can combine this into a single log statement saying it's log base 5 of the product of these two arguments, which is u cubed times v to the fourth. And we're done. All right, now the next one's an interesting problem because when you go to use your calculator, you'll find that there's only a common log button and a natural log button. There's not a log button for other bases on most calculators. So let's say you are allowed to use your calculator and you want to find out what is log base 2 of 7. Well, unfortunately, there's no easy answer for this. It's going to be an irrational number. But what we can do is use a technique where we use some of these properties to manipulate it to solve it. So let's call the answer to this, let's call that y. So y equals log base 2 of 7. You could have used x or any variable you want. Now, I'm going to take this equation, which is in logarithmic form, and rewrite it in exponential form. So the exponent of 2 that gives you 7 is y. That means 2 to the y equals 7. And now, I'm going to take the natural log, or I can use any base I want, so I'm going to use one of them that is a button on the calculator. So when you're able to choose, personally, I like to choose natural log. I'm going to take the natural log of both sides. So the natural log of 2 to the y equals the natural log of 7. And now we see that all-important power property is what allows me to take exponents out of the, take variables out of the exponent. So this gives us y natural log of 2 equals natural log of 7. And now you just divide both sides by the natural log of 2, and that gives you finally something that I can put into the calculator. And when you put it into the calculator, this is what the display would look like. Natural log of 7 minus natural log of 2. Make sure you do close your parentheses for your arguments. You want to build that habit. And therefore, rounding to 4 decimal places, because you always have to answer the question being asked, means that the answer is approximately equal to 2.8074, rounding to 4 decimal places. And notice how we would say approximately equal to, because it's not exactly equal to. This expression would be an exact answer, and this number would be an approximate answer. Now, this method can be generalized. There's nothing special about the 2, and there's nothing special about the 7. Plus, when I made the choice to use natural log, I could have chosen any base I wanted. This is the basis for what they call the change of base formula. And one of the reasons why you see natural log used almost exclusively in higher mathematics is because you can always change any log base to natural log, since that's the one that shows up in most of the formulas in higher mathematics. All right, so let's look at a change of base formula, and we're actually going to prove it as well. And our proof is going to be the same method we used to solve that last problem. We're just going to do it with variables. So here we have log base a of m is equal to log base b of m over log base b of a. That's our change of base formula. Notice how the b can be chosen to be any base you want. And that's what makes this so powerful. So we're going to start with the left side here. We're going to let x equal log base a of m. Then we're going to rewrite this in exponential form. So the exponent of a that gives you m is x. That means that a to the x equals m. Next, I'm going to take the log of both sides, and I'm going to choose some base b. I can choose b to be anything I want. So that means log base b of a to the x equals log base b of m. And therefore, now I can take that x out of the exponent using that all-important power rule. Power property. And then you'll have x log base b of a equals, and on the right side, no changes necessary, just log base b of m. Now we're going to divide both sides by log base b of a, and that gives us x itself, which is what we originally started with, log base a of m, is equal to log base b of log base b of m divided by log base b of a. So again, you can choose to change your logarithmic expression into any base by using the change of base formula. All right, so looking at a similar problem that we did with the log base 2 of 7, let's this time let you guys try log base 5 of 89. So go ahead and pause the tape, try this one on your own and see how quickly you can get it. Okay, hopefully you have an answer by now. Using the change of base formula, we can quickly calculate this by noticing that your argument is what's going to go in the numerator, and your base is what's going to go in the denominator. And then you can change the logs on the top and bottom to be any base you want. Personally, I prefer natural log, so I'm going to make it natural log of 89 over natural log of 5. And putting that into the calculator, which would look like this when you do it, we can now, even though it didn't say it here, our directions were the same to round to 4 decimal places. So it would be approximately equal to 2.7889. And we're done. All right, this concludes our properties of logarithms, and we're done.